The broadcast is now starting. All attendees are in listen-only mode.
Hello everyone, and welcome to another Advanced Design Week series webinar. Today we are going to talk about the possibilities of advanced design for LC slabs and ribs design. My name is Kamil Dziedzic. I work in Gretek Poland office as a structural analysis engineer, mostly in the area of LC structures. So what we will actually discuss today are these three main topics, which is flat slabs design, so the slab supported only on the columns, slab with ribs, and so the slab that is firstly supported by the beams and later on the columns, and the deflection in the second phase. And by that I mean the cracked inertia, so how to calculate your total real deflection of your concrete slabs. So it seems like we are going to discuss mostly about the SE design, but what I will actually focus on is the FEM analysis, so the phase when you actually prepare your analytical model and get the real design efforts for your SC design. So how to get that, what to consider, and how it is done in advanced design. What are the tools for the job? So first of all, about the flat slab design. So you probably noticed that whenever you model a column connected to the slab, it's only connected with one central node. It leads to many difficulties, like we already need more finite elements in that area, and also it leads to the bending moment concentration. So you can't really tell what your exact design forces are. At the first attempt, you could just check the forces on the edges of your column, but this is really limited to several cases, like you need to have a particular cross-section shape, so the column can be only square or circular. The cross-section needs to be relatively small, so you can just check the force on the edge like it's 2 meters away from your central node. And there are other things to consider, and by that I mean not only the forces in the slab is what matters, but also the forces, like for example columns. So many software offer this solution only to get rid of the values inside the cross section, so you would be left with something like this. But imagine you have this cross section that is rectangular and you just get rid of the values inside the cross section. I don't really think that what we see now is the real design efforts, and it's not how our slab should work. Actually, the slab wants to support itself on the edges of the column. So the value we see in the middle picture, I believe, are real. So as you can see on the comparison on the right, you can see how far it stretches if it comes to the range of the bending moments. So you really need to rethink your reinforcement. So the values are nearly the same, but the shape of the design efforts is changed a lot. So how to actually deal with that? So what we could do to get the result as I show in the previous slide. You could actually model your column as a planar element, but you will lose the possibility to design your column with the column engine. Yeah, so you can just only design this as a wall. So it's not what we want. We will actually spend more time designing rather than saving our time. So we could do this fictional thickening of the slab at the column section. So again, this is a lot of work for us to do manually. So you cut the opening, you put another slab that is thicker. This is not the right tool either. So finally, you could use the master-slave Dove constraints. But this also, if you want to do it manually, you will have to do much work again. But this is actually automated, fully automated in advanced design. So how does the engine work? It actually consists of two automatic operations. The first one is preparing the mesh according to the cross section, and as you can see, it doesn't matter what cross section you use. It could be just simply rectangular or circular, but it can also be T section, L section, no matter what. As you can see, after the mesh preparation, the central node becomes the master node, and it's connected to its slaves at the edges. What does it lead to? First, let's see live how it works without the DOF constraint. So what we will get, what result we will get when we calculate our slab by default. So we just modeled some columns, modeled a slab. First, let's see the bending moments in the slab. So as you can see, no matter the cross section, the shape is the same, and it only leads to the high concentration on the central node. Let's also check the bending moments in the column, and please remember the value for the latent comparison. So it's around 20. Now let's see how to prepare the DOF constraints and how it will affect our results. So all you had to do actually is to specify in application options how far your range from the edge of the column to get your smoothing of the values and the master slave dove constraints. So this operation is actually automatic, so you only specify this range, and the dove constraints and the mesh is prepared at the edges of your column. So let's see the bending moments in the slab first. So as you can see, there is no more concentration, so the values you see are the real design efforts. And the cross section really matters. So we have this rectangular, and we have that another column that is much larger. So the shape of the design effort changes. Same for the L section we see. Now again onto the column, please see the bending moments in column. As you remember, the value was about 20. Now it's nearly 5 times higher. So you can't really not consider this. It's because the connection between the column and the slab is now much stiffer. So by the default, it's connected with one node only that actually doesn't have any size. So you need to consider the real connection between slab and your column because of the bending moments both in slab and in column. So imagine you would underestimate the bending moments in column 5 times. This would be really risky. So again, onto the topic with the slab with ribs design. As you can see, in every FEM software, the beam is modeled in the same plane as a slab. It's for the discretization, for build your analytical model. But this leads to underestimation of the beam stiffness, and also you will have to design your beam as a rectangular section. So what could you do are again few methods. The first one is the eccentricity, which you just change the analytical behavior of your beam. So you just offset the beam, and it's fine for the simulation of the stiffness. But actually, you can't design your beam anymore with the beam engine because you change the design efforts. I will talk about it in the next slide. Next, there is this stiffness increase, for example, using the Steiner's theorem. So you just change the inertia of your section just to simulate that the beam is beneath your slab. Again, you still have to design your beam as the rectangular section, so that's not all that you could do. Finally, there is this rib design engine, which is fully automated advanced design functionality, which actually consists of the offset method. So for the FEM analysis, the beam is modeled with offset, but at the design phase, the engine calculates the design efforts. And again, the beam is designed as a T-section, not as a rectangular section anymore. So if it comes to the eccentricity method, let's see in the two beams, one which is modeled by default and one with defined offset. So as you can see, the FEM analysis results actually changes with the beam with eccentricity. So the bending moment is really, really low compared to the default beam. So that's not what we wanted. Yeah, our beam is much stiffer now. So we expected higher design efforts. Yeah, but there is this axial force that appears in the beam, and it's because of the beam and the slab start working as a truss. So your slab is now the top chord, which is compressed, and your beam is now the bottom chord with is tensioned. So to get rid of that and get your design efforts real, you actually need to use the RIBS design engine within advanced design. So as you can see, you just model your beam as a linear element, your plate as a planar element, so nothing really changes. All you have to do is to actually define the effective width of the slab to make your beam work as a T-section. You can actually define it by hand if you calculate it yourself, or you can use the automated calculation according to the code standards. If you do that at the design phase, this engine takes into account many forces from the slabs, forces from the beam, and it all is reduced to the T-section gravity center. So your beam is now designed as a T-section with real design efforts, probably only bending moment. So how to define the effective width of your beam? As you can see at the beginning, there is no offset defined. I make sure my element is calculated as a beam, and I define the RIBS design calculation. As you can see, the offset is defined now. Before defining the effective width, I just check the span range for me to put in as a B1, B2. And so as you can see, the beam, the effective width beam can be calculated for single spans, if there is a possibility that would be different in each span, or as a single span. So now it's just a regular section. According to the local access, I can specify which effective width to define or which span range to define. If I only put B1, B2, the effective width and the height of the slab is calculated automatically. So let's see the design results for the RIBS design. I have this one beam that is designed as a standard beam and one beam that is designed as a RIB in my slab. So the results from FEM analysis, as you can see, behave just like the offset did. Yeah, so you can see this axial force and reduced bending moment, but actually the calculated reinforcement is higher in the beam designed as a RIB. All you have to do is to check the design efforts. So as you can see, even though in the FEM analysis results the bending moments were low, in the design efforts calculated with the RIBS design engine, you can see the real bending moment for your beam. And the beam is now calculated as a T-section. And on to the next topic, the deflection of slabs with cracked inertia. The keyword to that task are FEM iterations actually. So it's not only the design, but it also considering the preparation and calculation of your analytical model. So imagine the two scenarios that you don't actually need to calculate deflections. So at the beginning, you just calculate your FEM model, you get the design results, and you can calculate your SE section. So you get your reinforcement, you get your cracks. You don't actually get your deflection because that's not what you wanted to do. So the slab still for the whole calculation stays as no crack and no reinforcement is considered in the stiffness of this slab. If you want to calculate the real deflection, you can actually do some FEM iterations, which would consist both of FEM calculation and the SE design. And after the first iteration, you get your crack, so you can actually calculate your cracked inertia. So with that, you can update stiffness matrix and perform the second FEM calculation. Again, the SE design in the second phase would calculate the real deflection considering both reinforcement and both your cracked inertia. So there are few things that are important to mention in this task. So first of all, the calculation can be done with either theoretical or the real reinforcement. So you can just let the advanced design to calculate the required reinforcement, for example, for the ULS state, for the crack state, and calculate the deflection with that required reinforcement, or you can provide it by yourself and check how the deflection would change. You can actually see how the cracked inertia changes in your plate. Again, both with the required and the provided reinforcement. So you can see how stiff is your slab now. So at the beginning, it would, in the first phase, it should be just one. And so some places are reduced, but some places are even stiffer because there is no crack and there is reinforcement provided. And again, you can also consider your beams in the calculation of the slab deflection, because when you calculate the beam, it also has its inertia changed. So if the beam cracks, if the beam has some reinforcement provided, you can see the new calculated inertia that are taken into the second FEM analysis calculation. So first, let's see the slab design results for the first phase. So as you can see, I have some reinforcement calculated in my beams. I have reinforcement, theoretical reinforcement calculated in the slab, the bottom, top. With that reinforcement, I could, at the first phase, calculate the crack. So you can see the crack width in the beams, and also you can see the crack width in the slabs. I didn't do any correction to the crack, so as you can see, the crack width is nearly 0.6 millimeters. So that's not enough for me. I need to use more reinforcement actually. But for the calculation, I can set the correction of cracking. So the theoretical reinforcement would actually be provided enough to fill the crack. What I don't have at the first calculation is that I don't have the total deflection and I don't see the inertia changes with the crack, even though the slab and the ribs was cracked. So let's say right now I will calculate it with deflection. So I have to specify the iteration numbers. So as we said, at least it's 2. So I could put 3, I could put 4. I could even put one, but it wouldn't be the real total deflection considering the crack. So right now I have reinforcement calculated as well, but this time I set the correction of cracking. So my crack should be at least maximum 0.3 millimeters. So I can see now that both for beam and both for slab, I can see how the inertia changed. So fully cracked and non-cracked, and what is actually taken into the design would be the interpolated. So the mix of those two graphs. So where beam cracks, we use the cracked inertia, and when it doesn't, we use the non-cracked inertia. As you can see, we have same results for our slab. So we can see how the stiffness of our slab in the second calculation changed. So it's reduced by 30% in the spans and at the supports. So at the places where the biggest cracking is. So with that, I could calculate my real deflection, total deflection of the slab. The calculation was done with the theoretical reinforcement, but I could actually provide some reinforcement and check all the results. So I could see how much reinforcement I'm missing, what is the crack with the provided reinforcement, what is the deflection with the reinforcement. So I just checked some minimal reinforcement and do the calculation of the reinforced concrete again. So as you can see, now I have real reinforcement provided. I can see the ratio, I can see how much reinforcement I'm missing, for example, in the spans. So yeah, it's really a lot. So I know that I have to use some additional reinforcement in some areas. And I'm pretty sure that the slab is now really cracked. So we can see the values with the real reinforcement of the cracking. And we can finally see what is our total deflection with our real reinforcement. So as you can see, it's even increased because of the biggest cracking of our slab. So if you like the topic and you have any questions, you want to test it by yourself, please visit our webpage at gretec.com. You can contact also your local Gretec branch. Please also don't forget that at the beginning of June, we have this global digital conference. So the last year edition was really successful. There have been around 200 technical classes. So please don't forget, please register and be there. So that's it. Stay safe, everyone. If you have any questions, you can contact me anytime. If you have any question regarding the topic, you can ask them right away and to go to the webinar. So there is this question about the rib. Does the deflection of the slab take into the account the stiffness of the rib? So I actually answered that so you could see the cracked inertia of your rib. You could actually mix all the engines we presented today. So if you calculate the beam as the rib, it also would consider the cracking and it would be considered in the deflection of the slab. There is this question where we change the mesh for the column. I believe you ask about the densify of the mesh. I use the point to make my finite elements smaller at the central node. You will have the access to this presentation because it's recorded. I believe this will be put it on the website. There is this question about the master slave nodes. So I didn't really define any mesh I didn't prepare the mesh by hand to make the master slave nodes. I would have to if I done it by hand, but if you want to just do it automatically and just set the option in the results tab for the automatic DOF constraints at the columns, and you just specify the distance from the edge. So the mesh is actually prepared automatically, and the DOF constraints also are defined automatically. You don't have actually change your inertia. There is this question about changing the inertia manually. If you set the auto calculation of the inertia of cracked element in the second phase, it will change automatically. If you would like to perform only one iteration of calculations, then you have to change the inertia at the beginning by hand. And in the second phase, it's calculated automatically, so you don't have really to do it. Okay, I believe that's all questions. If I missed something, I will reach to you. So thank you for attending, and see you.